Hi, everyone. I will talk about static delayed sampling for probabilistic programming languages. And it's a compile time approach to optimize a given probabilistic program. So we might, to improve the efficiency of the inference, we might use conjugate prior relations between the random variables of a model. And, sorry. And for example, if we have a beta distributed random variable and a Bernoulli distributed observation on top of that random variable, then using the conjugate prior relations between this beta and Bernoulli distributions, we can calculate the posterior of theta in a closed form solution. And this can be done manually, but for large models, it will be error-prone and time-consuming. And other way is doing this automatically, as in delayed sampling approach. And this approach uses conjugate prior relations to make it more efficient during runtime. But it has to introduce some graph to maintain these relations. And it means that it introduces some runtime overhead. So then the research question is, how can we apply this approach at compile time to reduce the runtime overhead? And the main challenge about this approach is the expressiveness of such an algorithm, because in static time it's tricky to support loops, branches, and indexing. And our proposed solution to this challenge is following a conservative approach. We may not optimize all the parts, but we can support some parts, such as indexing. There are other compile time approaches, but the main problem with them is they are either specific to a sampling algorithm or a language, or they require some computer algebra, and which makes it hard to implement. And in our approach, we aim that we will not depend on any specific inference algorithm, and we can work on any universal probabilistic programming language, though we might be conservative. And our research approach simply consists of 3 steps. And in the first step, we take a probabilistic program and generate a graph out of it, which we called programmatic Bayesian network. And this programmatic Bayesian network is just an extended Bayesian network that allows us to encode everything that a Bayesian network cannot encode directly, such as function calls, loops, and this kind of structures. And after generating this programmatic Bayesian network, then the transformer takes this graph and then transforms it into a more efficient form using conjugate prior relations between the random variables. And after that step, we reconstruct this generated optimized PBN and reconstruct the probabilistic program. So on the left-hand side, we have a code written in Mike and CorePPL, which is a probabilistic programming language. And on the right-hand side, we have the PBN generated from this code. And first 2 lines are just let bindings that binds a function call and a float number to variables. And we create a code block node to represent that. A code block is just simply a function that takes an input and then outputs random variables. And in this case, the code block P will output A and B. And next, we have a categorically distributed random variable. And on line 4 and 5, we have a list of random variables, a Gaussian distributed random variables. And each of these random variables depends on the output from code block P. So basically, we put a multiplexer to select the appropriate output and then put that into the corresponding parameters of the distribution. And we have on line 6, we have a random variable mu that we get from a random variable. And then it has a stochastic indexing. And for that, we are putting a multiplexer node. Actually, this is kind of the important point, because with this support, we can use the conjugate prior relations in models such as latent Dirichlet allocation. And next, we have an observed random variable that depends on the mu. And we see that actually there is a conjugate prior relation between the observed random variable and mu via this random variable list, because both are Gaussian. And next, I will not go into details of this transformation, but it's on the left-hand side, we have the generated PBN, and on the rightmost side, we have the transformed, more efficient form that we get by marginalizing and then conditioning on the observed value. And on the final part, we have the optimized graph, and on the right-hand side, we just generate the code from this optimized graph because we have everything that we need to generate this probabilistic program. And finally, on the left-hand side, we have the original program, just to compare, and on the right-hand side, we have the transformed program. And in transformed program, observed random variable is marginalized, and we condition on the observed value. Thus, we were able to reduce variance at compile time.